Conduction is the transfer of heat from one molecule to another through the body. The particles vibrate about their mean position and do not leave their mean position. Good conductors have particles vibrating at higher speed than poor conductors. Metals are generally good conductors, whereas wood is a poor conductor. Conduction is the transfer of heat from one molecule to another through the body. The particles vibrate about their mean position and do not leave their mean position. Good conductors have particles vibrating at higher speed than poor conductors. Metals are generally good conductors, whereas wood is a poor conductor. Convection is the transfer of heat where the molecule travels. This is observed in liquids and gases. As the molecule heats up, its density decreases and it travels upwards, and its place is taken by a cooler molecule. The molecule which traveled to the top cools and comes down again to replace a hot molecule which is moving up. This sets up a convection current. As hot air goes out from the chimney above the fire, the cool air comes to take its place. This sets up a convection current. If ice is put at the bottom of a test tube, it does not melt when heat is applied as shown. This is because the heat transfer is taking place through convection and the convection currents do not reach the ice. The land gets more heated than the sea and cools faster than the sea. This is because the specific heat capacity of water is very high. In the afternoons, the land gets heated much more than the sea. The warm air on the land rises, and the cool air takes its place. This sets up a land breeze. At night, the land cools faster than the sea, so the sea is warmer than the land. The hot air rises above the sea, and the cool air from the land takes its place. Radiation is another form of energy transfer, but unlike conduction and convection, it does not require a medium. Black bodies absorb radiation at a faster rate than white bodies. Therefore, on hot days, it is preferable to wear white clothes. Dull surfaces absorb radiation at a faster rate than shiny surfaces. Shiny surfaces reflect a lot of the radiation that is incident on them. The bulb on the left is painted black. It therefore absorbs more radiated heat from the candle than the bulb on the right. Since the left bulb gets warmer, the vapor pressure in the bulb increases on the bulb on the right. This creates an imbalance in the levels of water in the two arms. a black body will also emit heat at a faster rate than the white body. A black body absorbs and emits heat at a faster rate than the white body. But in general, the rate of absorption is higher than the rate of emittance. That is why the temperature of a black body will be more than that of a white body. A dull surface will emit heat at a faster rate than a shiny surface. A dull surface absorbs and emits heat at a faster rate than the shiny surface. But in general, the rate of absorption is higher than the rate of emittance. That is why the temperature of a dull surface will be more than that of a shiny surface. If you just had a brick wall, heat will pass through by conduction. If you had an air wall next to the brick wall, it will pass through the brick wall by conduction and through the air wall by convection. If you have a vacuum in the air wall, it will stop the conduction and convection, since both of them require a medium. It will not stop radiation though, since that does not require a medium. If you just had a brick wall, heat will pass through by conduction. If you had an air wall next to the brick wall, it will pass through the brick wall by conduction and through the air wall by convection. If you have a vacuum in a thermos flask, a vacuum separates the inner wall from the outer. If a solid wall was used instead of a vacuum, the heat would have leaked out by conduction. If an air wall was used, the heat would have leaked out by convection. By using a vacuum, conduction and convection are eliminated. But radiation can take place through a vacuum, since it does not require a medium. So the inner walls are polished shiny, so that all the radiation bounces off the walls, and that stops the heat leakages completely. If you want to stay warm in a room where the surrounding temperature is very low, you have to minimize the heat transfer from the outside. By having a single wall, conduction would take place. By having two walls separated by air, conduction takes place through the walls and convection takes place through the air chamber. If you replace the air with styrofoam, which is a poor conductor, it cuts out conduction and convection. The glass house allows visible light of short wavelength in. The plants and the soil get heated, and the longer wavelengths of the infrared radiation are unable to go out through glass. The trapping of this heat results in a higher temperature inside. The heat, which would have been normally lost by convection, is retained. When a solid is heated, it expands. The amount of expansion depends on the temperature it is heated to, its original length, and the material it is made out of. In the summers, you will see wires between poles sag. This is because the wires expand due to the heat. Liquids expand in volume on heating. If you measure the levels before and after heating, you will notice a difference in the levels. Water density increases as it is cooled. But as the temperature decreases to 4 degrees, a strange thing happens. Between 4 degrees and 0 degrees, the density of the water decreases as it cools. As lake water gets in contact with freezing surrounding temperatures, its density increases and it settles at the bottom. However, between 4 and 0 degrees centigrade, the density starts decreasing, and the top layer stays at the surface and does not sink. The top layer freezes, while the water below remains at 4 degrees. Fish and plants can thus survive. Without this property of water, the lake would have been an ice block. Heat capacity is the amount of heat required to raise the temperature of the substance by 1 degree centigrade. If you heat 1 kg of water so that its temperature rises by 1 degree centigrade, you will require a certain amount of heat. This heat is the heat capacity of the 1 kg water. If you want to raise the temperature of 3 kg of water by 1 degree, you will require more heat. So we can say that the 3 kg water's heat capacity is more than the heat capacity of 1 kg of water. Specific heat capacity is the amount of heat required to raise the temperature of 1 kg of the substance by 1 degree centigrade. Heat capacity of 3 kg of water is more than the heat capacity of 1 kg of water. But the specific heat capacity of 3 kg of water is the same as the specific heat capacity of 1 kg of water. Specific heat capacity depends on the substance and not the amount of it. Water has a very high specific heat capacity compared to most substances. To increase the temperature of 1 kg of copper by 1 degree takes very little heat in comparison to the heat required to raise the temperature of 1 kg of water by 1 degree. Heat always flows from a body with higher temperature to a body with a lower temperature until the temperatures of both bodies are the same. Even if a tiny body has a higher temperature than a huge body, the heat will flow from the tiny body to the huge body. When heating ice, you notice no change in temperature until the whole ice is melted. Once the ice has completely melted, the temperature goes up as it is being heated. This will be clear from the graph. When naphthalene is heated up to 80 degrees, you will see a rise in the temperature. Once the naphthalene begins to melt at this temperature, although heat is supplied, no rise in temperature is noticed. Once the naphthalene has completely melted, the temperature begins to rise again. As naphthalene starts cooling, you see a drop in temperature until 80 degrees. Naphthalene begins to solidify at this temperature. Until it completely solidifies, the temperature remains 80 even though heat is being removed from it. Once the naphthalene has completely solidified, the temperature begins to fall again. As heat energy is increased, the molecular vibrations increase. This increases the internal energy of the body and raises its temperature. During a phase change from, for example, liquid to gas, the amplitude of vibration remains the same. Therefore, the temperature also remains the same, but the distance between the molecules begins to increase. During a phase change, for example, liquid to gas, heat is supplied to the body, but its temperature does not increase. This heat is being used to change the state from liquid to gas. Once in the gaseous state, if you keep supplying heat, the temperature will increase. For substances which contract on melting, like ice, pressure reduces the melting point. For substances which expand on melting, like wax, pressure increases the melting point. When impurities are added to a substance, the melting point decreases. When impurities are added to a substance, the melting point decreases. The boiling point of a liquid increases with pressure. The pressure cooker boils water at 120 degrees, which reduces the time taken to cook the food. This also saves gas. The boiling point of a liquid increases with pressure. The pressure cooker boils water at 120 degrees, which reduces the time taken to cook the food. This also saves gas. The boiling point increases by adding impurities to the liquid. the boiling point increases by adding impurities to the liquid.